Physicists once believed that motion was about paths in three-dimensional space. Hamilton's formulation of classical mechanics showed that the real story unfolds in an abstract, higher-dimensional stage, now called phase space. Here, every point represents the entire state of a system. Motion becomes a flow, and conservation laws become geometric statements. In a previous video, I presented the original work of Hamilton, which refined the Lagrangian formulation of classical mechanics by treating generalized coordinates and their corresponding canonical momenta as independent variables. I showed how the single second-order Euler-Lagrange equation gets replaced by the two first-order Hamilton equations, which exhibit two noticeable features. First, the time evolution of one variable is the derivative of the Hamiltonian with respect to the other variable. And second, this minus sign. These two equations look quite symmetric, except for the annoying minus sign. But as I will show you in this video, these two features lead to a very important theorem. The profound significance of Hamiltonian mechanics lies in its mathematical structure, revealed when the dynamics of a physical system is presented in a space defined by the canonical variables. We call this phase space. This is not our three-dimensional space, but instead an abstract multidimensional space where the axes are Q and P. For a physical system of n degrees of freedom, phase space has two n dimensions. For this reason, phase space can only be properly visualized for systems with a single degree of freedom, in which case the phase space becomes two-dimensional. Let's introduce a new variable, z, specifying the state of the system as a point in phase space. Note that this point on phase space tells us simultaneously the position and momentum of the system. Now we can study the evolution of the state of the system by calculating how the state changes with time, z dot. This is some sort of velocity in phase space. Remember, this is not the velocity of the particle in our three-dimensional space, but the velocity of the state of the whole system in this abstract phase space. Now, here comes the Hamiltonian magic. Since the components of z dot are q dot and p dot, then z dot becomes this, which shows that the time evolution of the state of the system is completely determined by its Hamiltonian. We will extend this to more dimensions, but for now let's look at a few examples. Consider a free particle. Its kinetic energy is 1/2 mq dot squared, which also defines the Lagrangian. From here, we calculate the canonical momentum p, and following Hamilton's method, we invert this to write q dot as p over m. And from here, we get the Hamiltonian to be p squared over 2m. Let's explicitly calculate the components of z dot. Given the form of the Hamiltonian, we find that z dot has no vertical component, and its horizontal component only depends on p. Consider the origin of phase space. This represents the system at the origin of the spatial coordinate q having zero momentum. Since p equals 0, z dot is 0 and the system does not evolve. It just stays there. Note that it doesn't matter where the object is. If p equals 0, it just remains there, as expected by Newton's first law. Instead, consider the system with some momentum. Now the velocity, z dot, has a horizontal component, which is proportional to the momentum. This is how the phase space of a free particle in one dimension looks like. Quite boring, but it reveals the idea of a flow in phase space. As a second example, let's explore the harmonic oscillator, as usual. This is the Lagrangian, and following the same steps of the previous example, you can confirm that this is the Hamiltonian. Now the velocity field is more interesting because it depends on P and Q, meaning that its magnitude and direction will change depending on where in phase space the system is. The origin represents the equilibrium position of the oscillator at rest, so nothing happens. But let's explore what happens when the oscillator is taken away from equilibrium. At this point, P equals 0 and Q is positive, so Z dot has only a vertical component pointing down. At this other point, Q equals 0 and Z dot has only a horizontal component along the negative direction. This corresponds to the oscillator going through the equilibrium point at maximum speed. On the other side, P equals 0 and Q is negative, so Z dot has only a vertical component pointing up. A complete cycle of the oscillator is represented by this ellipse. All these concentric ellipses represent the same oscillator with different initial conditions. Since the total energy of the oscillator is given by the amplitude of the oscillation, bigger ellipses represent the same system with increasing amounts of energy. This should not be surprising, because the form of the Hamiltonian is exactly the equation of the ellipse. The harmonic oscillator is represented in phase space by concentric ellipses that correspond to level curves of the energy of the system. Another interesting example is the simple pendulum, which is represented by very interesting curves in phase space. 3 Blue 1 Brown has an excellent video showing all the details from a mathematical point of view with mesmerizing animations. If you want to see dazzling flows in phase space, make sure to check his video. No matter what textbook you look at, any presentation of phase space is followed by a very important result known as Liouville's theorem. The true impact of Hamiltonian mechanics in physics was unveiled by the great German mathematician Carl Gustav Jacob Jacobi. Just a few years after Hamilton's paper, Jacobi recognized a connection between the evolution of the canonical variables in Hamilton's theory and a theorem published in 1836 by the renowned French mathematician Joseph Liouville. Liouville's work was not on mechanics. He made significant contributions to number theory, complex analysis, differential geometry, and topology. Together with Lagrange, Laplace, and Legendre, Liouville is the fourth giant L of French mathematics in the 19th century, and for some reason the only one left out of the celebrated names on the northwest side of the Eiffel Tower. Liouville's theorem describes a method for solving a particular system of differential equations. Let me show you what Liouville did. He was interested in the solution of a system of m first-order differential equations that can be written in this form, where wj are the m unknown functions and p sub j are general known functions. Liouville demonstrated that if the system of equations is solved in terms of a collection of integration constants a sub j, then the determinant of the matrix, whose entries are the partial derivatives of the solutions with respect to the integration constants that Liouville called u, is a function that satisfies this new differential equation. That's Liouville's theorem. An interesting but purely mathematical result. No relation with mechanics, Hamiltonians, nor phase space. In 1842, just a few years after Hamilton's paper, Jacobi recognized that the evolution of the canonical variables in Hamilton's theory is precisely of the type considered by Liouville. To understand Jacobi's finding, let's take the n coordinates and n momenta of a general physical system of n degrees of freedom and arrange them into a single state vector Z. Instead of the two-dimensional space of the previous examples, now the phase space has 2n dimensions. Just as with the 2D examples, we can calculate the velocity field in phase space as z dot. Note that this vector is analogous to the W sub j equations of Liouville. Jacobi rederived Liouville's result for a mechanical system by replacing W with the state vector z, setting m equal to 2n and the functions pj to z dot. This is the equation for the determinant u according to Liouville's theorem. Let's focus on the sum and expand it for the first n and the second n terms. This allows replacing z by q in the first sum and z by p in the second sum, where now the index k runs over the n degrees of freedom of the mechanical system. Here, Jacobi imposed that the system is described by the Hamiltonian equations of motion. This is when the two features mentioned earlier, that the time evolution of one variable is the derivative of the Hamiltonian with respect to the other variable, and the relative minus sign, become crucial. Because after rearranging terms and using that the order of derivatives is irrelevant, we find that these terms perfectly cancel each other out. Since the canonical variables satisfy Hamilton's equations, this whole sum is a zero. And with this, the time derivative of u is also zero. Liouville actually ended his paper with a comment for the particular case of a vanishing sum. He wrote that if the sum happens to add up to zero, then the determinant u is a constant that can be chosen to be equal to 1. The way to do this is by writing the m integration constants in terms of the unknown functions evaluated at a particular earlier time that we can call t0. With this, the definition of u becomes this expression. Evaluating this matrix at t equals t0, we get the identity matrix, which has determinant 1. And since u is constant, it must be equal to 1 for all times. Jacobi gives Liouville the credit for the original theorem, but emphasized that Liouville did not realize the benefit this theorem offers for integration. What Jacobi discovered was that Liouville's theorem for Hamiltonian systems implies an unexpected conservation law. As a physicist, I find this sum very interesting for its analogy to flow. Let me show you what I mean. When you take the derivative of a vector field along each coordinate and add them, you get a number defined in vector calculus as the divergence of the vector field. For a velocity vector, the divergence measures flow behavior at each point. A negative divergence represents a flow that tends to become more dense. On the contrary, a positive divergence at a point represents a flow that tends to become less dense. A velocity field with zero divergence implies that the fluid is incompressible. From our previous result, we know that a Hamiltonian system evolves in phase space as a divergence-free flow. This result has a profound consequence. A collection of points within a region of phase space can evolve, changing shape, but its density cannot change. This is usually stated as the volume of an element of phase space remains unchanged under Hamiltonian evolution. This is what every textbook calls Liouville's theorem, despite this being only the consequence of Liouville's theorem when applied to a Hamiltonian system discovered by Jacobi. In 1866, under the guidance of Joseph Stephan in Vienna, the young Austrian physicist Ludwig Boltzmann was finishing his doctoral dissertation on the kinetic theory of gases. Boltzmann found the Hamiltonian formalism and the vector space of canonical variables the ideal playground for his description of the motion of large numbers of molecules. Boltzmann described a collection of molecules by their corresponding volume in phase space. An element of volume at time t0 is given by this expression. After an infinitesimal amount of time dt, this volume is given by this. Relating these two volumes as a coordinate transformation, we get this relation, where J is the so-called Jacobian of the transformation. In case you are not familiar with this important concept, in general, when we transform coordinates, we need a way to account for distortions produced by this transformation. The Jacobian is a function that compensates for nonlinearities at each point. Consider Cartesian coordinates x and y. The infinitesimal element of area is just dx times dy. If we instead use polar coordinates r and theta, the element of area is not just dr times d theta. The correct expression has an extra factor r. But where does this extra r come from? It can be understood geometrically as the product of dr and the small arc given by r d theta. But this approach only works in 2 or 3 dimensions. For a more general approach, let's calculate the Jacobian of this transformation. The two coordinate systems are related in this way, so you can quickly confirm that the Jacobian matrix is given by this. From here, the Jacobian, this is the determinant of the Jacobian matrix, becomes this, which simplifies to just R. This is the origin of the extra R found above. The great thing about the Jacobian is that it works in any number of dimensions, where the geometric approach would be unthinkable. Back to Boltzmann. Let's simplify these expressions by only looking at a simple system of 1 degree of freedom. The volume is an area in this case. The components of the Jacobian matrix are defined in this way. To evaluate them, we can write Q as a Taylor series, keeping only leading order terms. Using Hamilton's equations to replace Q dot, we get this. The same procedure can be done for the canonical momentum. Now we can explicitly calculate the derivatives needed for the Jacobian matrix, where the approximation here denotes that quadratic terms in dt are neglected. The Jacobian matrix becomes this. The final step is calculating the determinant. Once again, we neglect high powers of dt. Here we encounter the difference that probably reminds you of Jacobi's calculation. As before, these terms perfectly cancel each other out because the order of derivatives is irrelevant. Boltzmann concluded that at leading order, the determinant of the Jacobian matrix is 1, meaning that the phase space volume remains unchanged over time. Boltzmann was not aware of the work done by Liouville and Jacobi. He independently rediscovered this fundamental theorem and published it in 1871. In a follow-up paper, Boltzmann cited Jacobi. At this point in history, the mathematical derivation of the theorem was completed, but the name phase space did not exist yet. As David Nolte describes in this great article, it was in his follow-up paper where Boltzmann makes the analogy of the fluid-like paths in this abstract space and the so-called Bowditch-Lissajous figures, which are two-dimensional patterns that emerge when plotting two harmonic time series against each other. They are easily generated in oscilloscopes or a pendulum with 2 degrees of freedom, sometimes used in artistic creations. In the generation of these patterns, one crucial parameter is the relative phase between the two time series, and a point in these figures is called the phase point. In 1872, Boltzmann borrowed this word to characterize the changing position and momenta of molecules. This is how the word phase in phase space entered physics. Maxwell published in 1879 a paper about Boltzmann's work on energy distributions, in which he emphasized that phase is the word to describe the n-coordinates and n-momenta of a system. Boltzmann published his lectures on gas theory in 1896, where he credits Liouville for the discovery of conservation of volume in phase space. This is why every textbook calls it Liouville's theorem, but maybe we should call it the Boltzmann-Jacobi-Liouville theorem. In the year 1911, one of Boltzmann's students, Paul Ehrenfest, and his wife, the physicist Tatiana Afanasieva, published an article reviewing Boltzmann's work. It is here that the word phase space appeared for the first time. The study of phase space volumes might be counterintuitive, but it is crucial in statistical mechanics. Note that the volume conservation theorem does not imply that the density of states is uniform throughout phase space. In fact, Boltzmann discovered that regions of phase space can be more or less populated depending on the energy and another physical property called temperature. It is interesting that the volume in phase space for each degree of freedom has units of action, just like Planck's constant. With the advent of quantum mechanics, some fundamental principles got updated. The Boltzmann-Jacobi-Liouville theorem got replaced by a principle called unitarity, and the role of phase space of classical mechanics was taken by a linear vector space of states called a Hilbert space.